So good afternoon. Today we will see some practice question of structure analysis. So we will see a total of 12 questions. So here are the question 1. All the questions that we will solve. So now we solve the question one by one. So for question number 1, we have to find the support moments of this beam. So A is the fixed support, B and C is the roller pin joint, roller pin support. So we will solve this through slope deflection method. So for this, first we have to find the fixed end moment. So for span AB, a 100 kilonewton force is applied at the midpoint of the span AB. So through this we find that the fixed end moment of AB is 62 and fixed end moment at B is 62.5 negative. So for span, similarly for span BC we find the fixed end moment, and so second we have to construct the member equilibrium. For this, here is the equation of member equilibrium. So theta and theta B is the angle between angle after deflection at A and B, and as the A is fixed support, so theta A is 0. Here also theta is 0, and through this we got the two equation for span AB and two equation of span BC. So we get total of 4 equation. Then we construct the joint equilibrium. So at joint AB, the total moment at joint B equals to 0. So and total moment at joint C equals to 0. So from this, so moment at B is 1 is question 2 and 1 is equation 3. When we both add, then the joint equilibrium moment of at point B is 0. So through when we solve this equation, then we got two values, this, and at joint C we got this equation. When we solve this equation, we get the value of EI theta B and EI theta C, and through by putting all these value in above equation we get the moment. To solve the equation we get the moment, and then we draw the bending moment diagram. For this, the maximum moment at span AB is WL by 4, that is 125, and maximum bending moment at BC is WL square by 8, that is 140 kilonewton. Then we draw this, and when at bending moment at the A, B and C we find through this, and then moment at A is 46.8, moment at B is the moment at C 0. Then we connect the lines, so these are the bending moment diagram. So when we draw the deflected shape of the beam, then it comes out to be like this. And first part it is negative, so it is like this, and second it is positive. Here it is at B, bend deflects 0, and then here, so deflected shape of the beam is like this. Now we will solve the same question with moment distribution method. So for moment distribution method, in first step we have to find the fixed end moment. So fixed end moment we have calculated in the above process also, so this is the same. And then we have to find the distribution factor of the beam, of the joints. So for that we have one joint B, and in one joint we have member AB and BC. So here is the member AB and here is the BC. Then K comes out to be, for the fixed support, 4 EI by L, that is L is 5, so 4 by 5, and for BC it is pin support, so that is 3 EI by L. So if we find the summation of both these, comes out to be 2, and distribution factor is K by summation of K, that is 0.4 and 0.6. And in third step we have to distribute moment. So for joint member AB, BC we write the distribution factor, and then fixed in moment, then unbalanced equation. If we sum these two, the unbalanced moment comes out to be 31, and in here 93. So we have to balance the moment, so we have to apply the negative moment in that joint. So the moment is distributed through this distribution factor 0.4 and 0.6. So we multiply the negative 31.25 with 0.4, that is comes out to be 12.5, and here it comes out to be 18.75. Then half of the moment is comes to the opposite end of the member. So 12.5 is half, 6.25 comes out to the point A, and here 18.5 comes out. So here it not come because of the 3I by L, that is the joint C is the pinned joint, so no moment is carried to the other end. Only the moment of B is carried to the moment at C is carried towards the point B, that is 14.87. Then in next expression also at point B we have unbalanced moment of 46.875. So we again apply negative of this moment to both the member. So it also distributed according to this distribution factor, and then 18.85 comes out to be here. And again the moment, half moment does not go to this side, but because it is pin joint, and half of the moment is come in this side because it is fixed, so 9.3. After that we sum all the moment of this part, and it's come out to be 46, and again through this and this, so total moment of this beam comes out to be this. So in this method also we get the same moment, that is 46, 93, 93 and 0, and through the slope deflection method also we got the same moment. Sorry, here the answer is somewhat different. No, this is fixed in moment. Here moment is comes out to be the same, 46, 93, 99. Now we will see the question number 3. In this question we have A and D as fixed support, and B and C as pin roller support, and the moment of inertia is vary. So for first step we have to find the fixed in moment. So for span AB the load is not at the midpoint, so the moment at AB is WABL square, WAB square by L, and it comes out to be 35, and for AB WBA square by L, that is comes out to be minus 17.7 kN. Similarly for span BC 66.67, and CB negative of that. And then in step 2 we have to find the member equilibrium. So at member equilibrium we have to use this equation, and here theta is 0 as A is fixed support, theta is not 0. Similarly applying this equation we find the member equilibrium equation of this. Then we have to find the joint equilibrium. So at both this joint, like for this joint and this joint, moment is 0. At A and D's moment is not 0, but at B and C the moment of both the member is combined to be 0. So at joint B this should be 0, and by putting the value of these two we get this equation 7. And when we apply the joint equilibrium at C we get this equation. On solving these two equations we get theta EIB and theta EIC, and by putting all this value in the equation we got the following moments. And one of the method we can use to solve this equation is through matrix. Like we can form this matrix as 4 for equation 7, that is 4, here it is coefficient is 1, and we multiply I theta b, and here the equation is 1, coefficient is 1, 3, I theta b theta c equals to final result minus 48.97, here 46.67. Upon solve this matrix we get the theta ab and theta ac. Now we will see the same question 3 with moment distribution method. So for this also we have to find the fixed moment that we have calculated in the above question only. Then distribution factor we have to find. So for member AB, distribution factor is 4ei by 3, but here I is 1.55, so overall. And for BC, 4ei by 4, 4ei by L, length is 4, I is 2i, and here is 8, summation of k is 4, and distribution factor comes out to be 0.5 and 0.5. And for member CB, for CB, k is 4ei by 4, L is 4 and I by 2i, so here comes out to be, and for CD, ei by 4 comes out to be 3, and distribution factor is 0.67 and 0.33. Sum of these distribution factors comes out to be 1 at one joint. So then we have to, step 3, we have to do moment distribution. For this we make the table member distribution factor, fixed moment, then unbalanced moment at each joint. So at joint B, unbalanced moments comes out to be 48, and joint C minus 46. And then we apply the balance moment according to the distribution factor of both the member at each joint. Then each joint BA comes out to be 24.48, and here distribution factor is 6, 7 and 0.33, so it is distributed through that. Then carry over half of this moment comes out to this side, half of moment comes opposite member. Then also at joint B and C we get the unbalanced moment. Then again we apply the balanced moment in both the joints, and again carry forward, then again unbalanced, then we repeat the similar process until we get the carryover very less. Like after 5 step in this question we get carryover moment as 0.08, 0.1, 0.08, 0.05, so it is very less, like 0.0 something. So after this we stop the process and calculate the total bending moment at each member. So here we can see that at joint B the left hand moment is 52.82 and right hand moment is 53.02. so this comes out to be similar, like summation of these two should be 0, but hence we have stopped our iteration at 0.01, so some discrepancy come here, like some moment is not 0. But if we do this iteration at infinite time, then we get these two nearly equal, nearly similar. So here is the end moment of this equation. Through this end moment we can draw the bending moment diagram very easily. So next we see the question number 5. So this is some different question, like at A and D is fixed support and C is roller pin support, and one member is vertical at B and D is vertical. So similarly we find the fixed moment, like at AB distributed load, it is similar like as we have done earlier. For span BC it is also we have done earlier. In span BD it is vertical and moment is applied there, so we rotate this in, we see that being like this only, but it is rotated 90 degree. So through taking this only we will calculate the fixed in moment, and the at D fixed in moment is negative, and at B it is positive. In step 2 we find the member equilibrium. So we use this equation. So at A is theta is 0 as it is fixed support, theta B is not 0, then here we find the equation. Similarly, we find this equation also. Then we apply the joint equilibrium. We have only one joint at joint B, so we have these three forces comes out to be 0, and upon putting the value we get equation 7. And at joint C also, CB equals to 0 because C is pin joint. So at pin joint the moment is always 0. When we do this, then we get equation 8. Upon solving equation 7 and equation 8, we get theta IB and theta IC as 2.42 and 18.79. Upon putting this theta IB and theta IC in the above equation, we get the bending moment at each joint. And now we will see the frame analysis. So it is the frame where D is fixed support, A is pin support, D uniformly distributed load applied at the top, EI is 50 km force applied in this direction at mid spin of AB, and this is roller spin support. Similarly, here also we have to find the fixed in moment of all the spins. So AB like this, BC 60, 25. For spin CD, no force is applied in this span, so the fixed in moment is 0. Now we will calculate the distribution factor. At joint at AB, it comes out to be 4 EI by L. So L is 4, I by is 4I, and here it comes out to be this. Here also this is same, so all is same. So all the distribution comes out to be 0.5. Finally, we find the moment, member, distribution factor, fixed in moment, unbalanced force comes out to be 35, 60, negative 60. Distribute the load half in both the member at each joint. Then carryover moment here no carryover moment pass because point A is pin support. Point A is pin support, so no carryover moment comes in this end. And similarly, we do the filtration, and after filtration carryover moment is very small, like 0.1, 0.0. So now we will stop our expression and we sum the moment at point A. As it is pin support, the total moment comes out to be 0. At B, both are nearly similar, 4, 2 and 5, 5, little bit different, and here also. So after this, all the moment at each joint comes out to be at A it is 0, at B here negative, here positive, at C and at D. So this is the final answer. Now we will see the end moments of this equation. Here A is fixed, C is fixed, E is pin joint, F is roller pin joint, B and D have 3 member. Now similarly we find the fixed in moment of each in span. So span AB, BC, BD, DE, FD, all we find the fixed in moment and distribution factor. We have total of 2 joints at joint B and joint D. At each joint we have 3 members. So for all the member 4 EI by 4, 4, 4 all here. Like here we have 4 meter. So distribution factor 4 EI by 4, 1 and 1 and 1 and 1. Summation case 3, so all the distribution factor comes out to be 0.33. So now we will find the moment distribution of S. So joint A, B, C, D, E, F. A, B, all the members. At joint B we have 3 members, A, B, B, D and B, C. At joint D also we have 3 members. Now distribution factor 0.33, all have 0.33. Fixed moment, we write it here. Unbalanced moment, at joint B we have total of summation of this, we have 10 kilonewton of unbalanced moment, and at joint D we have 35. Then I will distribute this load according to its distribution factor. So 0.3333 comes out to be at each joint. Then carryover moment at BA comes out at end A and BC at end C. Similarly here, then all no other moment is left unbalanced. So when we total the moment at each joint of each member, then we total moments comes out to be this, and here is the final moment distribution. Here at joint A 38, here it is pinned joint, so it comes out to be 0 at, so this is fixed. Now we will see the question number 8. So it is the frame structure. We have to find the horizontal displacement at C. So for this we have to find the support reaction. So we have 3 support reactions, AX, AY and DY. 20 kilonewton is applied here. So for support reaction we balance the summation of Fx power 0. So for this Ax plus 20 equals to 0, Ax is 20 kilonewton. For dy plus 0, moment is the, so we find all the support reaction, then we find the load of each member, like 20 kilonewton here, support reaction 20 20 20 for each member. So for each B, C, B, A and A, D we have 20 kilonewton member, and at B 20 kilonewton is applied here, 20 kilonewton here. So according to this we get force load on member BD as minus 28.28 kilonewton. So for if we want to find the horizontal displacement C, so we applied the unit load at C and find the load on each member due to this unit load at C. So then we find, and it load on each member comes out to be according to this diagram. Then we find the summation of N, L and L. So N is the load on member due to original load, N is the load on member due to unit load at our desired location, L is the length of the member, and this is the multiplication of all these 3 values. So we find this, and summation of NLM comes out to be 349.65, and according to the formula the horizontal displacement at C is summation of NL divided by A. So this is the final answer. A is the area of cross section of each member, and E is the modulus of elasticity. Now we will see the question number 9. Set 9 is question similar to the previous question, only little bit different, like A is fixed support, D is fixed support, B says distributed load, B and C is pin roller support. So for this we have find the fixed in moment on all the span. Then distribution factor, so at BA distribution factor is 0.43, at BC 0.57, at CB 0.53 and 0.47. So here 4ei by 4ei by all are fixable. So distribution factor is same formula for all the member. Then find the moment distribution method. So joint AB distribution factor is 10 here and fixed moment we can write here, and at joint B we get the total unbalanced moment of 26.25 and at C 7. So we distribute the load on each member on each joint according to the distribution factor, and we do the carryover on opposite side of the member. And again in second iteration the unbalanced moments comes out to be 1.89 and 7.84, and again we balance the moment according to the distribution factor on each joint, and again we get the unbalanced force, again we balance the moment, again we get the unbalanced moment, again we balance the moment, and after fourth iteration the carryover moment is very small, like point something. So here we stop our iteration and summation we get the moment, like here some differences comes because we have stopped there. If we continue this after infinite times it is same. After this we get the final moment. Now we'll see the question number 10. Here A is open, B is spin roller, C is spin roller and D is fixed joint. So for this find the fixed moment. At spin AB, one end is open, one end is fixed. So for AB, fixed moment is 0 and BA fixed moment is negative 30. For spin BC, it is linearly distributed load. So for BC, fixed moment is WL square by 20 and is 24. For CB, fixed moment is WL square by 30 because at BC, if we see from here the moment more force is at B side, so we divide it by less number. We can learn through this method, and at C less moment is here, so we divide by more number because at C moments comes out to be less and at B moment should be more because more force is towards the B side, like here. So through this intuition we can remember the formula for fixed moment for linearly distributed load. For spin CD it is quite similar, like point load, and then we find the distribution factor. As A is open, so distribution factor of A is 0 and at opposite it is 1 because sum of these two should be 1. And here for EI by L, I is to I, so according to this we get the distribution factor. Then moment distribution, so at AB, here BA distribution factor is 0 and 1, at C distribution factor is 0.27 and 0.73. Fixed moment we write all. Then at B, unbalanced moment is negative 6 and negative 6. Then we balance the moment through the according to distribution factor, it is 0 and 6. Here it is 1.62 and 4.38. Then carryover moment is here. This moment is do not carry over this at this end because B is pinned roller support and A is open, so no moment is carry on the B side at C. So in second iteration at B no unbalanced moment is there, and at C 3 kilonewton of unbalanced moment is there. So we balance this, and third iteration all the moments are balanced at each joint. So after this we get the final moment. In question number 11, it is similar to the question 10, but instead of fixed support at D we have pin support at D. So let's see what happens if we have pin support instead of fixed support. So fixed in moment is similar for all the similar also, but in distribution factor we have some difference. Like in earlier in CD there is 4 EI by L, but here SD is now the pin support, so at CD we have 3 EI by L. So because of this the distribution factor comes out to be 0.33 and 0.67. Now moment distribution method we have all the members, and at B we have distribution factor of 1 and 0, and at C we have distribution factor of 0.33 and 0.67. Now at B we have unbalanced moment of -6, and at C also we have unbalanced moment of -6. So we balance the moment according to distribution factor on both member and both joint. So at joint C we have 3, 2 and 4, and at C we have 0 and 6. Now here the moment carry forward towards this. Here the 4, this 4 does not carry over to other side because D is pin support. Earlier, when D is fixed support, then this 4 is carry over to this support in earlier question. So after second we have unbalanced moment of 8 at C, and we have 0 unbalanced moment at B. Now we again divide this 8 in according to moment distribution factor. Then after second iteration all the moment get balanced, and it final end moments comes out to be this. Now we will see this question. So here A is fixed support, B and C is pin roller support, and D is open. So we find the fixed moment. At AB there is no load, so fixed moment is 0. At span BC uniformly distributed load, so there is 20 kilonewton. And at span CD, at D is open, so here moment is 0, and at CD we have moment of 800 kilonewton. So distribution factor at CD it is 0, and at BA for EI val, at BC at C is pinned and D is open, so here it is 3 EI val. So we have distribution factor of 0.52 and 0.48. Now step 3 we have moment distribution. So at B moment distribution is this, and at C moment distribution is 1 and 0. Fixed moment is written here, and unbalanced moment at B is 20 kilonewton, at C 780 kilonewton. So we balance the moment according to the distribution factor, and at C also all the moments comes at CB. So half of the moment is come this side, and here half moment comes this side. Here 9.6 does not go to the end C because D is open at C is pinned, so no moment goes in this direction. So again after in second iteration we have unbalanced moment at B is 390, and at C we have no unbalanced moment. So after when we balance this, half moment come this, and now all the moment is balanced. After all this we have final in moment comes out to be this. Now we have solved all the 12 questions. Thank you.